that we can discuss. But I'm going to go to linear fit here. And this is the equation that we're using to produce our linear fit. So find our percent difference between where we would predict that ball to land using this equation at 0, 10, 20, 30, and 45 degrees, okay? If we go to our quadratic fit, you'll see that our line starts to bend when we input more measurable data points. So it's no longer just this linear fit, it's actually quadratic. So it bends, and so you can see that our equation is becoming quadratic right here, okay? And then if we go to a quartic, which is to the 4th power, we get a better linear fit, and we can tell that by just looking at this r squared value. It is equal to 1, and that's pretty much saying that this line is hitting each one of these points very well. And I want to say the center of each one of these points. So if you look here, this is not hitting the center as well. Our linear fit is pretty high. It's getting close, okay? And so if I go back to our precision analysis and I look at, what is this, the 30 degree and the 45 degree, you'll see that our linear fit is way out compared to our not our measured, but our kinematic theory here. And so we have our quadratic fit here, and we have our measured fit. So our measured range is pretty low compared to what we're about to see for our linear fit and measurement. If we go on over, you'll see that our percent difference between our nonlinear fit and measurement gets lower than our percent difference, but it's high. And then we have our percent difference between kinematic theory and our linear fit theory, which is around 18%, 17%. So we go from 9% to 23 to 13.4 to 17.4. Now look at what happens with our percent difference between our kinematic theory and our nonlinear fit. It's around 7.7. So I would definitely go with this one over, and it would probably be best to do it, comparing it to the measured range. I don't have that here, but it'd be nice to look at that. Maybe we can do that in class, but it would be nice to see that. If you look at 45 degrees, our theory is around 1.138. And you see our linear fit, our quadratic fit, and our measured range. It doesn't change much from this measured range. And so the percent difference is definitely getting higher between the kinematic theory and the measurement. And the percent difference between the linear fit and the measurement is huge, 46%, 46.6%. And then our percent difference between our nonlinear fit and measurement is starting to go down. And the percent difference between our kinematic theory and our linear fit is high. Whoa. And the percent difference between our kinematic theory and nonlinear fit, it's getting lower. And it's the lowest out of all of these things. I really wish I had the quartic up there because I don't have this equation in there. Maybe I'll give that to you guys as an assignment. But any two ways, that is the end of this assignment. Make sure you upload this. So I'm just going to say send link, of course, copy link, and then I'm going to upload this as just like in the usual fashion.